Hello and welcome. In this video, we'll be discussing a variety of different types of terms that you can include in a multiple linear regression. One of the biggest benefits of multiple linear regression is not just the ability to include multiple variables, but also to include multiple types of variables within a single analysis. Now, it's worth mentioning that you could do this in simple linear regression too, but for a variety of reasons, we weren't really able to take advantage of it. For instance, if we wanted to include a categorical variable, we actually have to break that up into several different variables, and simple linear regression could only have one variable, so we weren't able to do that. Same thing with things like curves. We actually have to include multiple variables in order to model a curvilinear relationship, and so we're not able to do that in simple linear regression. In addition to the regular old continuous variables that you'd kind of think of, three additional term options that we'll talk about specifically in this video. And actually, that's what this video is more on. It's not how do I include another categorical variable or not how do I include another continuous variable. You just kind of drop in another continuous variable in the model and interpret it. But the three new types of variables that we can include are categorical variables. And these are literally mathematically identical to t-test and ANOVA if we construct those particular comparisons. We can also include polynomial terms and more general curvilinear relationships. So if there's a curve in the data, we can actually model that with linear regression. And that's so cool. Again, y'all, this is Pandora's box. You look at your data, you say, what do I think is going on here? And then you run a model to test it. And you say, okay, I thought there was a curve. I'm going to test if there's a curve or not. And you can do a test and see, again, what does your test tell you? It says beyond the sample. I'm going to use the sample to make an informed decision about the population. Does the sample give me enough evidence to determine that there's a curve in the general pattern between these two variables, not just the sample, but in like the overall pattern based on what the sample represents? Again, so freaking cool, I think anyway. So polynomial terms, this is how we're going to address curves, and we're going to talk about how to do that in this lecture video. And then interaction terms. This is going to feel very similar to ANOVA, but interaction terms in multiple linear regression are just a little more complicated. Again, I keep saying the word Pandora's box in the sense that we open up a world of possibilities. A lot of our previous courses, you think of math people, you think of people who are really good at calculations or really good with their calculator or whatever. As we work through this, and again, as we get used to implementing this in software, I actually find some of the best analysts, some of the students who succeed the most in my most senior level courses are less those who kind of grew up doing calculations or are really good at math, and more those who are very applied and could just think creatively about situations. It's people who say, well, what if we took into account this variable? Or what if we looked at it from this lens? Those tend to be people who can look at data and find really unique and powerful insights. And so again, it kind of changes the game a little bit when we start dealing with all of these different types of relationships that we can include under the umbrella of an analysis that we're going to talk about in this particular course. Well, now, again, it's kind of open. You aren't limited to, oh, well, if it's a category, I have to remember the right test and then construct the test statistic. No, if it's a categorical variable and you know that that's what you want to include, you just include it because that's the appropriate thing to do. Again, you stop thinking about the statistics as much and you start thinking more and more about the interpretations and implications of what you're doing. And that's a big goal. We've been trying to lead up to that this whole course. Hopefully in some way we have, I guess we'll see. But in any case, we're going to talk about these three terms in this video, these three types of terms. We're going to briefly discuss them, just a couple of slides. This is the type of term. This is our approach. And then once we get to the implementation in R, we'll discuss how we implement these using software or R. All right, so it's worth mentioning that multiple linear regression is not set up to handle a categorical outcome. So I say a Pandora's box and we can do anything. Well, we can do anything as long as it's not a categorical outcome. Is there a regression to handle that? Yes, it's called logistic regression, and it can handle categorical outcome variables. But for multiple regression, that's going to be beyond what we can cover in our tools. Remember, if you have a categorical outcome variable, the recommendation is simply that you convert any continuous independent variables to categories and then use your chi-squared analysis, which looks at the relationship between two categorical variables to analyze it. What multiple regression can handle categorical variable-wise is categorical independent variables. So think about when we have an ANOVA, or a t-test, we have a categorical independent variable. A t-test, it has two categories, and ANOVA, it has two or more categories. And then we have a continuous outcome variable. Regression can handle that. A multiple regression can handle any situation that a t-test or an ANOVA can handle. And again, if we set up the test correctly, we'll actually get the exact same test statistic and p-value. Now, the process of implementing categorical independent variables in multiple regression involves something called coding the independent variable, or translating the categorical variable into numbers that can be put into a regression equation. Now, there's a couple of different procedures to do the coding, and I'll say coding has an impact on the interpretation of the parameter estimates in the final multiple regression. So we're going to code these in a couple of different ways. We're going to get a few different betas, and depending on how we coded the variable, the betas are going to mean some different things. In this course, we're going to discuss a coding procedure called dummy coding, and we're going to kind of leave it there. For a single independent variable in the model, again, it's the exact same to t-test and or an ANOVA. And we've discussed this before, but this actually means that the t-test and ANOVA are subsumed by multiple linear regression. And I should be careful here. While that's kind of true, typically we use the term multiple linear regression when we're talking about multiple continuous independent variables with our continuous outcome. When we start talking about mixing categorical and independent, you can still call it multiple linear regression, but sometimes a generalized linear model when we talk about ANOVA being subsumed by regression. Typically, we mention ANOVA subsumed by the general linear model, and regression is also subsumed by the general linear model. So all of these things fall under that broader umbrella. And again, I think this is pretty cool. It's kind of unifying all of the analyses that we've done this summer under one, all the analyses that we've done in this course under one umbrella. And so from this, again, the utility here is that we can start to combine these things when appropriate. We think less about, well, what's the right test, and more about, okay, this variable is the appropriate one to include. So I just include it. And then I focus on, okay, well, what does that mean in this context? What does it mean when I have a variable here and this variable also? And then again, remember, we do the interpretations after accounting for X and Y and Z, or I look at interaction terms, or I look at curves. I can look at all of that stuff and look at some really fun relationships with data and find some really interesting stories in data sets. So why do I use a multiple linear regression instead of a t-test? Like if I say these are the same, and that point stands for ANOVA too. If I say these are the same, why would I do this approach instead of a t-test or an ANOVA approach? Well, remember, in multiple linear regression, I can do the t-test variable. I can include the categorical variable for the independent variable and have the continuous outcome. That's a t-test. If the categorical variable has two categories, that's a t-test. But remember, in multiple linear regression, I can also add additional independent variables. So I could do the t-test, but then I could do that after accounting for demographic information, or I could do that after accounting for this really important other variable. So I can add other variables to add to the interpretation of the t-test. So that's why we might do it. Now, I will say that for me, when I conduct tests, I still do t-tests and ANOVAs all the time. I don't just always do multiple regressions. The idea is essentially, if I'm just looking at a categorical variable with two levels and I have a continuous outcome, I'm just going to use the t-test. If that's all I care about and if that's all I'm looking at, I'll just use the simplest test because it's the simplest test and it's simpler to interpret. If I have a categorical independent variable with multiple levels, say 3 or 4, and a continuous outcome, I'll just use the ANOVA. So if I am in the appropriate situation for a t-test or an ANOVA, I probably still just we'll use the t-test or ANOVA. But in a situation where I want to do that and also account for other things, multiple regression gives me the flexibility to do that that's not available in a t-test or an ANOVA. I make it sound like the interpretation in multiple regression is more complicated, and it is a little bit. The interpretation's the same, but we have to set it up, usually using the F-test for nested models to do the test, especially with an ANOVA situation. A t-test, it's just kind of built into the cake, so you don't have to worry about it. Again, I tend to prefer just the more straightforward analyses when possible, and use the multiple linear regression when I want to take into account those other categorical or independent variables, or excuse me, categorical or continuous independent variables. All right, so we mentioned we do dummy coding. How? Well, what is dummy coding? Well, dummy coding is pretty easy, actually. We're going to start in the case of binary variables. So binary is just two options. So think about like male, female, or something like that. We just have two potential options, treatment or control, two options. So binary variable. And for binary, it's going to involve eventually 0 or 1. Sometimes this is called one-hot coding too. All right, so first we have to decide which is going to be the reference category, the one you want to compare to. And this is actually an important decision for dummy coding variables with two options, binary variables, and when we get to dummy coding categorical variables with more than two options. Determining the reference category is important. So for a variable on sex, male, female, I might pick male as the reference category. So now if I do a comparison, female will be comparing to male. What I'll do then is I'll make a new variable for the dummy coded categorical variable, and I'll name it the other option. So if male is my reference category, the new variable's name is going to be female. And in this new variable, it's going to contain ones and zeros. It's going to contain a 1 whenever that particular participant is female in this particular case, and it's going to contain a 0 whenever they're not. So let's look at a quick table on this. For participant 1, they're male. My dummy coded variable, I chose the reference category of male. And so I made the dummy category, or the dummy coded variable, it's named the other category. So the reference category is male. The variable name is the other one. So the variable name at the top there is female, the other one from the reference category. All right, so now for female, for the female variable, I just go down, and anytime the participant is a female, I put a 1 in the female new column. And then anytime the participant is not a female, I just put a 0. So for this first participant, they're a male. So under the female column, they get a 0 because they're not female. For the second participant, they're female. So under the female column, they get a 1 because they're female. So one hot coding means it's going to be 1 indicating hot. That is the presence of that particular option. So the presence of female is a 1 in this case. And again, in the eventual analysis, we're going to be comparing to the reference category. So my females are going to be comparing to males. All right, so in our regression model, we're going to not include the original categorical variable with male, female. Instead, we're going to include the new dummy coded variable we made. So we'll include the female variable that we made. The parameter estimate for the female variable, the beta that's in front of it, now indicates on average how much higher or lower the category is in terms of the dependent variable than the reference group. So if we're looking at, say, I don't know, wage, then we would look at how much higher or lower the female wage is than male. So in this particular case, a positive number, female compared to male, would indicate that females are higher than males on average, and a lower number, a negative number would indicate that females are lower than males on average. In a model with only one independent variable that's been dummy coded and is balanced, that means the sample size in both groups is equal. The parameter estimate is going to be the mean difference between the variable category and the reference category. So that is, if I just looked at the mean of male and the mean of female, then the beta 1 estimate, the B1, is going to be the mean difference between those groups. One other thing to note that I don't think I mentioned else on here is in the case with just one balanced and dummy coded variable, while B1, if in the case of just one, you have beta 0, you have beta 1, and that's it. That's all you have if you just have that one variable. Beta or B1 is the mean difference between male and female. But remember, B0 is what happens when the other variables are 0. So remember, if my female, the variable I included as the independent variable, is 0, that represents a male category. So B0 in that case, the intercept, is actually the average male score. And so that's, again, why it's important to pick the reference category. That defines what the intercept is referring to. And it also defines the nature of the relationship that your parameter estimate for B1 is studying. This is, in our case, studying the effect of female compared to male. Positive meaning females are higher, negative meaning females are lower. So essentially, in a broader scale, you can think of this as adding the parameter estimate for that categorical variable whenever the observation is in the category. So whenever it's female, you add that beta, and then whenever it's male, the female binary variable turns to 0, and so that beta value just turns to 0 and disappears. So that beta value only pops up when the participant is female, and then whenever the participant is male, that value just disappears. The significance of this determines if it is significantly different than the reference category, and you can take that as the interpretation. So a statistically significant finding for that particular parameter estimate, that is the beta next to the categorical variable, that would indicate that females are statistically significantly different than males. Statistically significantly higher if the beta value is positive, and statistically significantly lower if the beta value is negative. Oh, and I did mention that at the end here. I didn't remember if I did. So the intercept is when all the independent variables are 0. And remember, when the female is 0, that is the reference category. So that's what the intercept is referring to. All right, so let's discuss a polynomous variable. So polynomous is just a very fancy way of saying a categorical variable with more than just 2 options. And these can also be included in regression. So in that first one, the tests, remember I mentioned a hypothetical case where we just had one independent variable that was binary coded. In that case, that is mathematically identical to a t-test. The test statistic is going to be the same as the t-test statistic. The p-value is going to be the same p-value as a t-test. So that's a t-test. In this case, with more than 2 categories, now we're talking about ANOVA. The test, and we'll talk about it in a second, the test by default is not the same, but if we use the f-test for the nested models, we can get the same test as our ANOVA. Now, as before, when we have multiple categories, so let's say a person's hair color, let's use brown, blonde, black. In this case, we start by defining a reference category. This is the category that everything else is going to compare to. So pick something that you want to compare everything else to. It can be any of the categories, and if you're using software and you just stick in a categorical variable without defining your dummy variables, it'll just pick one either at random or the first one alphabetically or the first one that it sees, depending on the software, to use as the reference. But it is worth taking a moment to think about what is the best reference category for your data set and your situation. All right, so after you pick your reference category, you're going to make not just one dummy variable, but you're going to make multiple dummy variables. Let's say we pick the reference categories people with brown hair. We're going to make a dummy variable for all of the other groups, for the blonde and the black hair people. So if I had 4 variables and I picked this first one as my reference category, I'm going to make 3 dummy variables. I'm going to make one for each of the categories that's not the reference category. So here, again, k variable options, I'm holding up 4, so 4 is k. I would have pick 1 for the reference category, and then I would have k minus 1 dummy coded variables. So I would have 3, in that case, dummy coded variables. For each of these, I would go through and I would mark a 1 if the participant fell within the category, and a 0 if not. So if I'm doing hair color, brown, blonde, black, Again, I use brown as my reference group, so blonde and black. I would, for blonde, go through, and any participant that's blonde, I would mark a 1, and for everybody else, I mark a 0. For black, I would go through and mark anybody as a 1 who has black hair, and then a 0 for everybody else. So again, doing the 1 where it's there and 0 not, so the 1 hot coding for each of those variables. All right, so in this case, we're considering a categorical variable with the most recent outreach method. This was kind of an interesting study. We're looking at attribution modeling. So in this case, phone, mail, or online. We want phone to be the reference group. Okay, so I have phone, mail, online. Phone is the reference group, so I need to make 2 categories, one for mail and one for online. And I'm going to name those variables those different levels. So I have a variable for online and I have a variable for mail. For each of them, I'm just going to read down, and if it's online, I'm going to, in the online column, I'm going to write a 1, and otherwise I'm going to write a 0 for everything else. In the mail column, if it's mail, I'm going to write a 1, and I'm going to write a 0 if it's anything else. So this first participant, the outreach was phone. In the online column, I score them a 0, and in the mail column, I score them a 0. And that's correct, by the way. This person doesn't get a 1 in any of the dummy coded variables here. They're in the reference category, and the reference category has all 0s for all the dummy coded variables. That is correct. That seems a little bit weird maybe for the first time, but that is correct. For the second participant, they are online. That was their most recent outreach method. So the online column, I mark them a 1, and the mail column, well, if they're online, they weren't mail. So in the mail column, I mark them a 0. The third participant, similarly, their outreach method was mail. So in the online column, they get a 0, and in the mail column, they get a 1. And I would just go through the rest of the data set and do that marking. So in the regression model, I actually include all of the dummy variables I made. So all of the k-1 dummy coded variables, I include all of them in the regression model. Now, each of them are going to have their own associated betas, and each of those betas compare that particular category to the reference category. So for instance, if I'm comparing, in my last example, phone was the reference category, mail and online were the other 2 categories. So mail and online are both going to be included in the model, and they're both going to have their own betas. The beta for mail is testing mail versus the reference category, which was wait, what was the reference category? I'm getting confused. Yeah, phone was the reference category. So the beta for mail would be testing mail versus phone. So that would be the magnitude would be on average, how different is mail versus phone in terms of whatever Y is, say, amount of sales. And then a test of significance would say, is mail statistically significantly different than phone? The online, the same thing. It would be the average difference between online and the reference category, phone, and then a test would test, is online significantly different than phone? So again, for reference category, because all of these things are testing and comparing to the reference category, you do want to pick a reference category that you want to do a bunch of comparisons to. If you pick a reference category that you don't really care about, then all of your comparisons are not really going to be particularly useful. With that said, even if all of your comparisons are not particularly useful, it is worth mentioning that you can test the categorical variable as a whole. That is, the categorical variable, what's the last outreach method? I can test that all as 1. How do I do that? Well, I actually do that using that F-test for nested models. Remember, I can test multiple independent variables joint contribution with the F-test for nested models, and I can pick which independent variables I want to test. So if I wanted to test this categorical variable, I would pick the mail and online outreach. That's the 2 dummy variables from my outreach method categorical variable, and I would pull both of those out and see, is that model any worse for having removed these? If so, then these things were important to have included. Now, I'll mention that we're only pulling 2 of the dummy-coded variables out. This does test the joint contribution of all 3 options. This does test the entire contribution of the whole categorical variable. And in fact, if you do that test, because this is an f-test, that'll be the exact same statistic, test statistic and p-value, as your f-test from your regular ANOVA. All right, so one limitation here is there is no way to test the variables that are included, the dummy-coded variables, versus each other. They only test against the reference group. So let's say I did the phone as the reference group, so I have online and mail included in my model. There's no way to test online versus mail. Now, with that said, if I really wanted to, I could redo the dummy coding and make, say, mail the reference group, and then I could do a comparison between online and mail. But that's kind of a pain. So ideally, just pick a good reference group and check that out. Or if you don't really care about any particular pairwise comparisons between the group, then you can just do that nested f-test to test the overall contribution of that categorical variable to see, did that categorical variable contribute in any way in general. But if you do want to do pairwise comparisons and you do care, then I'd recommend that you pick a nice reference group, or a reference group that you care about the comparisons to, because that way you don't have to redo it. All right, so let's change gears a little bit from our categorical variable inclusion and talk about polynomial terms. So remember, polynomial terms are like x squared and x to the third power and stuff. And these can be included in multiple linear regression. When these are included, they allow us to look at relationships between x and y that don't follow a strict line. Typically, these are, well, not typically, these are powers of a predictor variable. So I take an independent variable, and if I have multiple independent variables, I can do this with one of them. I could do this with all of them. And I raise it to different powers, say x squared or x to the third. And again, this lets me model curvilinear relationships, relationships that look like curves. So for instance, if I had a quadratic curve, if it looked like it was curving like this, or maybe the other way, curving up and down, my model would look like y equals beta 0 plus beta 1x plus beta 2x squared plus epsilon. Again, it's weird, but this is considered a linear model because the coefficients, that is the betas, are all don't have powers. So when the betas are not raised to any powers, this is considered a linear model, even though this lets us look at curved relationships between x and y. All right, a couple of notes when you do this, and actually it really is pretty simple. You just drop in the term. But rule number 1 is you always have to include lower order terms. And what I mean by that is you have to include the lower powers if you include a particular power. So for instance, if you wanted to put in x to the third, you would also have to include the lower powers as separate terms. So I'd have to have an x squared term, and I'd have to have a regular x term. If I'm testing if there's a significant curve, I only look at the test of the highest order term. So if I'm doing the x to the third thing, I start by interpreting the x to the third and see if that is significant. And if not, I would remove it and potentially rerun the model. Or if it was a theoretical reason, I might keep it in. But really, when I'm interpreting this, if I'm interpreting if there's a curve or not, I only look at the contribution of the curvilinear components. That is the x to the third, and then maybe the x squared. If x to the third wasn't significant and I removed it, then I might look at x squared by itself. If a power of 2 or greater is significant, and we'll talk about this in a second, but I don't interpret all the coefficients on this one. I just look at the highest power term. And again, if it's a third, then I might remove it, rerun the model. Now the highest power is a second. I would look at the coefficient of the second one. And if that's significant, or if the x to the third was significant in the first test, that would indicate that there's a significant curve in the data and that you should probably keep the polynomial in. Now, beyond looking at the highest powered term, I recommend not trying to interpret the parameter estimates. It's not that they can't be interpreted, and depending on something called the way that you define the contrasts, you can actually get reasonable interpretations from these, but as a rule, these are tricky, and the utility of these, again, it's not that there's zero utility, but the utility of these is maybe less than some of the other things we do. Again, if I'm doing polynomial regression, the idea is that there's a curvilinear relationship between A and B. And that's kind of the conclusion. Now, I will say you can use these for prediction, but with prediction, be very careful about extrapolating. Remember, extrapolating is predicting outside of the range or the joint range of your independent variables. Again, prediction is fine to do, but you just need to be real careful about extrapolating with polynomials, because polynomials are notoriously bad for this, especially as you get near the edges. They kind of tend to drop off or shoot up. And that's usually a very, very, very bad prediction. So be careful about extrapolating outside the range of your data. Last but not least, I'll recommend that you don't go crazy with these polynomial terms. For the polynomial terms, I would recommend sticking to, maybe a squared if you think there might be a little curve in the data, maybe an x to the third if it looks like there's a wiggle there for some reason. I would recommend trying to look for a theoretical connection rather than just looking at data and kind of saying, oh, I think that might be it. I mean, you absolutely can with data, but trying to figure out, hey, does squaring this particular units, I'm looking at money, does dollars squared really mean something in this context? Is there a reason that would or should make sense? Those theoretical reasons can be really, really important. So I would recommend theoretical support. If you're just playing around with it, again, x squared, x to the third, that's where I would max out. Without strong theoretical support, I wouldn't go much beyond that. And ultimately, it's because that just adds a lot of confusion, especially as you get near the tails. As you add a whole bunch of things, they just shoot off faster and faster and faster at the tails, which might make any extrapolation completely inappropriate. All right. Well, last but not least, let's talk about interaction in multiple linear regression. So as with two-way ANOVA, when we deal with models that can handle multiple independent variables, we can include interaction terms. To include the interaction term with two continuous variables, or even with a binary coded, a dummy coded variables and a continuous variable, we multiply them together literally, and then we include that product as the new variable to drop into the model, and then we're going to calculate its parameter estimate, the beta for it, and that beta is going to be the test of the interaction term, or the test of that beta is going to be the test of the interaction term. So we literally multiply variables together and include that product as a new variable. Just like with polynomial terms, where if we include a higher order effect, we also have to include the lower order effects. With interaction effects, if we include an interaction term between, say, A and B, we should also include A left alone and B left alone, the main effects of A and B. So just be aware of that as you're building your interaction terms. As with ANOVA, if there's an interaction effect, you need to be very careful about interpreting the main effects. The typical recommendation is just don't interpret them, and instead look at interaction plots. As long as it's just a two-way interaction. Typically, we don't include three-way interactions because they're just too complex. Actually, that's not true. I have interpreted a three-way interaction professionally, but beyond that, I don't know that I've done. I might have done a four-way interaction one time. Beyond that, I've definitely never done. But they just get really, really, really confusing to wrap your mind around as you get into higher level dimensions of interactions. So for interaction plots, it's worth mentioning interaction plots, while they're not too bad to create if one of the independent variables is categorical, they can be pretty tricky if both independent variables are continuous. Essentially, what we do is we make categories. We select a few options from the one of the continuous variables to kind of make it categorical for the purposes of the interaction plot to see what's going on. But yeah, it can be a little trickier if both independent variables are continuous. All right, here's a new and very important wrinkle. And I can't beat this drum loud enough because I feel like while people kind of know this in some ways, it's not really accounted for or discussed maybe nearly as much as it should be. And here's the idea. Adding an interaction term, whether it's statistically significant or not, it can be the most insignificant interaction term ever, but just including it anyway drastically changes the interpretation of the main effects. So including the interaction between A and B drastically changes what the parameter estimate for both A and B mean, even if the interaction isn't significant at all, because it's not about whether or not the interaction is significant. It's about how the math now changes. And so the interpretations of the coefficient of A and B are now extraordinarily different if the interaction term is included. So that's huge to pay attention to here. It's also worth mentioning if we don't include an interaction term, and I can't remember if I mentioned this later or not, but if we don't include an interaction term, that itself is a statistical assumption now. Not including an interaction term statistically assumes that there is no interaction. So if you're not sure, I'd recommend including the interaction term. That way you can test it and see, is there an interaction or is there not an interaction? And we'll talk about how to address the drastic change in interpretations in the main effects in a second. So don't let that intimidate you. Do let that raise flags if you see an interaction term. Make sure that you've done the adjustment so that the main effects are interpretable. But do realize that it's probably better to include interaction terms and find out that they're not significant than to not include them. Because if you don't include them, you're making a statistical assumption that they're not there, and you're not even testing the assumption. If you include it, at least you can test, is it there or is it not? And if it's not there, then you have evidence. Hey, there wasn't enough evidence to determine that there's an interaction, so I'm going to move forward assuming that there's not. And that way you can justify that decision a little bit. So when in doubt, include it, but do make sure that you're paying attention to this component right here. That is, that the interpretation changes. So again, whether or not the interaction is significant, I can't say this enough, whether or not it's significant, even if it's not significant, it's the most insignificant interaction term in the world, but it's in the model, the main effect interpretation is now changed. What changes about it? Well, the main effect interpretation changes to when the other independent variable is 0. So let's look at an example. Beta 0 plus beta 1x plus beta 2x2 plus beta 3 x1 times x2. And again, x1, x2, literally they're multiplied together. That's the interaction term between x1 and x2, and literally they're multiplied together. Beta 1 previously, if we didn't have the interaction, would have been, as x1 increases by 1, y increases or decreases by beta 1. But now beta 1 is x1 increases by 1, y increases by beta 1. When x2 is 0, it assumes x2 is 0 now, and that's new. That's very, very, very new. In our previous stuff, when we accounted for multiple variables, we said after accounting for the other variable, and that worked. It was kind of averaged over all of the levels of the other variable. But here, with an interaction term, whether significant or not, just the fact that it's in the model in the first place, this changes the interpretation of the main effect. Beta 1 is the main effect for x1. Beta 2 is the parameter for the effect of x2. It changes those interpretations to be, for beta 1, the change in y per unit change in x1 when x2, the other variable, is 0. Now, if x2 being 0 is nonsensical, that's kind of bad luck for you, because now x1, the parameter estimate for it, is only written in terms of when x2 is 0. And so, again, if x2 equals 0 just doesn't mean anything, well, now your test for beta 1 doesn't mean anything because it's at a level of x2 that just is unusable. Also, whether or not the x1 equals 0 or x2 equals 0 are sensible, if you don't know that this is going on, can create very deceptive and confusing results. So it's good to keep in mind. All right, so what do we do? Hey, my x2 equals 0, that's nonsensical. That's nonsensical. So does that just mean my test for x1 is not usable because it's done at a level of x2? that doesn't mean anything? Well, no, there's actually a procedure that we can use that we've already talked about that's going to come in and really, really help. So remember the centering procedure from the simple linear regression. What centering was we take all of our independent variable values or all of our variable values and subtract the mean. What this does is it moves the middle, or that variable equals 0, to now be the mean value instead of 0. So for instance, if I take, let's say I'm looking at weight and height, and I'm looking at the relationship, I'm trying to predict weight using a person's height. So weight is my dependent variable, height is my independent variable. Let's say I have something else that I'm accounting for, I don't know, hair color, and I'm trying to do this interpretation. I do an interaction term, and so now hair color is interpreted when height equals 0, and that just doesn't make any sense at all. And so what I want to do is I want to do this centering thing. So what do? Well, I take my height values and I subtract the mean of the height values. That new thing, I'll call it new height. Where height equals 0 literally meant you were 0 inches tall, new height equals 0 means you're at the average height. So now when I include this, and it's important to remember this doesn't change the interaction estimates. This just changes the values that it's related to. But now if I do this for both of my independent variables, the interpretations of their parameter estimates are much better. It's still when the other variable equals 0, but now the other variable equals 0 means the other variable's at its average value. So in our case that kind of sponsored this, the change in y per unit change in x, as x changes by 1, what's the change in y? And now it's when x2 equals 0, but if we centered x2, that's the same thing as saying when x2 is at its average value. And that does have a meaning. That actually is a very useful interpretation and a very useful test to run. So interactions. When we have an interaction, we have to be careful. If the interaction is statistically significant, we want to be careful about interpreting main effects anyway. We want to do an interaction plot. But even if the interaction is not statistically significant, in regression, it changes the interpretation of the main effects, just the variables left alone. Whereas in ANOVA, we could just go on and interpret the main effects, not thinking about it. In regression, we have to be a little bit careful. One solution is just to use centered values. That is, for each independent variable, I subtract its mean and then use that new version of the independent variable in the original's place for each of my continuous values. Categorical values you don't have to worry about as much, but for each of my continuous values. And in that case, now I still have to do the interpretation for the one when the other variable is at 0. But now when the other variable is at 0, if I use the centered version, means the other variable is at its average value. And so the interpretation for each of these parameter estimates makes sense. All right. So what happens? All that happens when we don't have a significant interaction. What happens when we have a significant interaction? So in that case, well, we can have a couple of different breakdowns depending on the structures of the independent variables. So remember, each independent variable can be either categorical or continuous. Now, I'll mention we discussed the case where both independent variables were categorical in the ANOVA lecture. So I'm going to leave that one. And if you're curious, you can go back and recheck out the ANOVA lecture set. Now, if you have one categorical and one continuous, one of each for your two independent variables, I would recommend in your interaction plot letting your x-axis be your continuous independent variable and let the distinct lines in your interaction plot be for the different categories. So you'll have different lines, a different line for each category, and then you'll have your continuous independent variable and your dependent variable will be the structure of your interaction plot. For two continuous independent variables, I would put the independent variable that you're most interested in on the x-axis. So if you have one you're interested in and one you're just accounting for, then the one you're interested in will go on the x-axis. And on the y-axis, you'll just have your outcomes like normal. Now, once you have this set up, your first variable as your or one of most interest. We'll call it variable 1, independent variable 1 on your x-axis, your y on your y-axis, your dependent variable on your y-axis. The second independent variable, we're going to break into groups so that we can make distinct lines as if it was categorical. So essentially, we're going to categorize the second independent variable only for the purposes of the graph. So not for the purposes of the analysis. The interaction term in the analysis is still treating it as continuous, but for the purpose of visualizing it, we're going to break it into categories. Now, there's a few different ways to break it into categories. One common one that I have seen and kind of like, it works out all right, is to select 3 different categories. I'll take that second independent variable, and I'll say, all right, I want to take it at its mean value. That's the first category. The second independent variable, 1 standard deviation below the mean. That's a second category. And the second independent variable, 1 standard deviation above its mean. That's the third category. So essentially, I'm going to have 3 values for each of those 3 categories, and I'm going to use those 3 things to create the 3 lines. We'll look at an example in a second, and maybe it'll help make sense. After calculating these, I'll look at the x and y relationship for each of those 3. I'll have, again, 3 lines based on those 3 levels of the second independent variable. So remember, when there's a significant interaction, the whole point interpretationally is that the impact of one independent variable on the outcome depends on the level of the other. So remember that we have to keep into account that when we're interpreting, it depends, the interpretation depends on the other variable. It's also worth remembering this, especially in the case where we have 2 continuous independent variables, but it's equally important if we have, say, 2 categorical independent variables or 1 of each. And that is, interaction terms are omnidirectional. Just because term A and B interact, and I say, oh, A's relationship to Y depends on B, well, yeah, that's kind of true, but it's also true that B's relationship to Y depends on A. So interaction terms go in both directions. Neither are right in the sense that they're only right. Neither are wrong, maybe is a better way to say that. They're both happening together. So is it one, is it the other, or is it both? Well, it's all of those put into a single number. That's your interaction. So an interaction doesn't on its own tell you which one is impacting which other one. Your study design might help to create a situation where you can tell which one is the effect that's being influenced by an interaction term. But without additional information, the interaction term itself is omnidirectional. It doesn't specify which one is doing the affecting and which one is being affected. All right, so let's do a couple of examples. So I'm going to put up 2 models, both of which are estimating miles per gallon, one of which is showing the interaction between a vehicle's weight and the engine design, which is a categorical variable. It's either a straight design or it's a V design. The other model, and we're going to look at the interaction plot here, shows an interaction between the vehicle's weight and its horsepower on the miles per gallon. So on the left here, you can see that this is the case where I have my my weight, my independent variable 1, my miles per gallon, my dependent variable, and I have different lines for my different categories in the categorical variable. For the straight engine, as the vehicle increases in weight, the miles per gallon decrease faster than in a not straight engine, in a V engine. So in this case, that would be my interpretation. The interaction, what's the relationship between weight and miles per gallon? Well, it depends a little bit in the sense that if it's a straight engine, there's a larger negative relationship, and if it's a V engine, there's a smaller negative relationship. I say it depends a little bit because the story of the graph is still relatively similar in that both of them have a decreasing relationship. So whether or not it's a V or a straight engine, both of them, the miles per gallon decrease as the weight increases. For the continuous plot, I have horsepower. And so I've got weight, my first independent variable, my miles per gallon second independent variable, miles per gallon, my dependent variable, and horsepower is my second independent variable. Again, this one, I broke it up into different categories. This middle category is the mean horsepower. This red category is 1 standard deviation less than the mean. So this is kind of a low end of the horsepower, but still in the group. Again, it's only 1 standard deviation below. And then the green is 1 standard deviation above the horsepower. Above the mean in terms of horsepower. So it's on the high end, but it's not like the peak. It's not like the minimum and maximum, though you could certainly do that too. In this case, I do the plot. I have my weight versus miles per gallon. I use my predicted regression equation, and I plug in these values for the different lines in horsepower. So for instance, for the horsepower for the blue line, I would just plug in 146.69 for all for the horsepower. When drawing this line, I'd plug in a whole bunch of different weights. I'd run a whole bunch of different miles per gallon. I'd color them all blue, draw them on the plot. And for each of those, horsepower is 146.69 the whole time. In this case, you can see as horsepower increases, the relationship between weight and miles per gallon decreases. And this is an interesting and potentially more fascinating finding than this engine breakdown, because I don't have all the horsepowers here. It just says as horsepower increases, the relationship with miles per gallon, the negative relationship decreases. Now, I will note what's really happening here. Well, what's really happening here is as horsepower increases, the overall miles per gallon itself decreases. And so we just never had many miles per gallon to start with at a low weight, high horsepower. We're at a very low miles per gallon. At low weight, at a low horsepower, we had a lot of miles per gallon. And so it had a lot more room to decrease. So that could be an interpretation here. But either way, this is how we would create the interaction plot, and, you know, a couple of ways that we might try to interpret that. All right, team. Well, I guess we'll wrap it up here for the different types of terms that we can include in multiple linear regression. Again, this lecture is really the heart and the meat and the coolness. It's the diamond in the middle of the whole thing of the awesome stuff that we can do with multiple linear regression. And the coolest part is we can do it all at the same time. I can include categorical variables. I can look at curvilinear relationships. I can account for interactions between variables. I can do all of this. And so when you can do all of it, again, the particular technique becomes a little bit less interesting. I could just do all of it. What we start to think about more is, okay, well, what should I do? What am I trying to think about in terms of the problem? What do I think is happening? And based on that, what should I include in my statistical model to test and see if that is happening or not? And how do I want those interpretations to look? So that's the cool part of multiple linear regression. All of this stuff, you can do all of this in addition to the regular old continuous variables that you can drop in just like simple linear regression. You can do a whole ton of them. You can do 10 independent variables. You can do 30 independent variables. You can do as many as you want. And again, all of this relates to the interpretation and the context, which brings us to essentially, how do I interpret this? What do I look at? What is the interpretation of this? That's the whole goal for this course. I hope we've been building up to there with you as well. Less and less and less on computation, and more and more and more on what does this mean? When might I use this? Why might I want to use this? And what can I get out of this to make my interpretation of a statistical model into something that can really help me make an informed decision? Alrighty, ladies and gents, well, thank you so much for sticking with me in this video. Today, in this video, we talked about how to do a couple of different things. We talked about dummy coding. How do we include categorical variables, independent variables, in a multiple linear regression? We talked about using polynomials. How do we model curves with multiple linear regression? And I just think the curves are the coolest thing, because now you can look at any data set and essentially fit a regression model to it. So how do we do curves? And then how do we do interaction terms in multiple linear regression? So that's what we talked about today. Thank you so much for sticking with me through this video, and I will look forward to catching you in the next one.